Hello and welcome. This is a LXL M1 Mechanics Unit 1 for NXL November 2002, and this is obviously question number 3. Now this question, just to give you a bit of an overview before we start the question, this was really making sure you understood what a velocity time graph was. What the gradient of this graph represents, which we'll go into, as I said, as one of the questions, and sort of understanding what the area of a velocity time graph represents. So all about it, so the gradient, the area, and how to draw one. So it's testing your full knowledge of this. So obviously we're going to be given some information beforehand. Now, as I said, I would advise either having the printout with the paper next to you, or having this as a separate tab on the computer while you look through the exam paper. But I'm going to give you the figures anyway. Just it's a bit more convenient for you if you have to watch me then. Okay, so we are told that your car accelerates uniformly from rest. So therefore, you obviously know, you don't need to know the rest of it. You just pick up a bit of information already. So we know the initial speed. Rest is another way of saying the car is stationary or at 0 meters per second. They all mean the same thing. Two-way speed of 20 meters per second in t seconds. Sorry. So therefore, we know at the first point I'm going to call this U1, okay? Because the first initial speed. So basically, this question is broken down into three sections. Three sections of speed of this car. So in the first part of this, and it'll become obvious when we attempt to draw the graph, the initial speed up is 0. The final speed, V1, so this is the initial final speed, if this makes any sense, and that is equal to 20 meters per second. And we are told in this time frame, so I put a little thing underneath, therefore time frame 1 happens within t seconds. So we don't know what this is. We could call this Z seconds or whatever, but we're giving it t, so we've got to use t. So use a different colour pen then. So in the next section, obviously the car is not going to suddenly change from 20 to 2000 meters per second, for example, in 0.000 seconds, because that's impossible. So therefore, the first part, the second section, as we're told, the initial speed is 20 meters per second. So I'll put U2 is equal to 20 meters per second. And we are told this is at a constant speed of this, so with no acceleration. So V2 equals 20 meters per second. Now you could put, and it'd be quite helpful, especially when we come on to talk about the gradient. You might want to put there A is equal to 0 meters per second. Okay. So I'm just going to check something on my camera. I think the focus is going to look a bit out. So I'm going to do this while I'm going live. How crazy is this? No, that should be alright. So I do apologise about the focus. I'll do it while I'm live here, so I don't have to pause the video. Okay. I'll pause the video anyway. I tried not to, but one sec. Sorry about that, just had to set the focus on that. So, therefore, as we said, in the second part, A was 0 meters per second. So that does help us in a way, and I'll explain it as we get on to what this question is actually asking. But as for this part, we're not just writing down what we're told. So that time period from U2 to V2 occurs where T2 is equal to 40. So the second time period occurs over 4 times the length of the first time period. That's another way of saying the initial part of it there. Okay? This is... Sorry, I think it's going to be funny. So I do apologise about that. The next part, so this is the last part of the situation. So therefore, we are told after 40 seconds, so after this period, after the second period, the object, the car in this case, decelerates uniformly. So I use a constant from 0 to so U3 is equal to 20 meters per second, because that's the last speed of the second section, to V3, which is the final velocity, which is rest, which is, as I said, another way of saying 0 meters per second. And this occurs, we're not giving this in t, now we're not giving this in 50 seconds. Now this would be nice if they were all in t's or all in seconds, but they're not. So when we come to ask in question A, part A, sorry, sketch a speed time graph to show the motion of the car, it's going to be a little bit difficult. Now what you need to understand, the first thing you need to realise, well, it's not going backwards, it's only accelerating or decelerating to rest, it's not going at negative velocity. So therefore we can consider the graph to be sort of like an x and a y axis without the negatives on it. Okay, so this is nice and obviously you would draw it bigger on your page. Right, so what I'm going to draw is each of the, actually, it's a bad idea. Well, actually we'll rub that out, it's a better idea. Just have a brainwave, this is just a curve. So I'm going to draw the axes in green, because I can. And the first part of the time period I'm going to draw in black, and the second part of the time period I'm going to draw in blue, so it will correspond with each time period. Okay. Draw this nice. Okay. So this is how you. So you're going to have velocity or speed. Doesn't matter which one you choose. Meters per second. I'll put velocity, and the y-axis is time. And we'll put that in t bracket seconds, because they mean the same thing really. T is in seconds, we assume, but obviously t is a given figure. So anyway, let's kick off with this. So we know the first part is initial at 0, so draw a little 0 there with the axis, and it's going to start from where 0, and we told it gets up to 20 meters per second, and the acceleration is uniform or constant, so we're going to draw a line of a constant gradient. Doesn't matter how high you draw it, you just need to draw a little dotted line across if you want to show them that, okay, this reaches 20 meters per second. You don't need to write meters per second there because you've already given it in the units. And what you would want to do there is draw like another dashed line down to say, okay, that occurs at t. So therefore what you're showing is there is a constant acceleration between 0 and t, and the final speed is 20 meters per second, which is what we're told in the first part. That occurs in the first part of this journey. So basically what we've done is use this information and put it on a graph. So we don't know what this gradient is yet, okay? Which is going to be quite key. So this next part, I'm going to draw in blue, and we told the initial speed is 20 meters per second, so we're carrying on from t, and the final speed is 20 meters per second. And, okay, so just propose that. So what you want to do is carry on this line, but do it as a straight line, horizontal, and draw a line down. Now what you can do is you can label that 5t, or you can label the distance between these two 4t. Now what I'm going to do is I'm going to label this 5t, and then put underneath between these two, so this is 5t take t equals 4t. Now you don't have to do that, but it doesn't specify it on the mark scheme, but I like to think it makes it nice and clear that where this blue line occurs, obviously you're not going to have a blue line on yours might be all black or whatever, or grey, whatever colour you have. Yeah, so that's what you'd use. I would do something like that to show there's a difference of 4t, so you're showing there is a 4t, but be careful not to put this second point as 4t, because yes, there is a difference between where this first part stops and this part ends of a time of 4t, 4 times as long as the first part. So obviously this part's got to be over a larger distance, but it doesn't need to be exactly 4 times whatever this is, because you can put not to scale, so you don't have to worry about that. But it's good, careful not to put 4t, because what you're saying, if you put 4t there, what you're saying is after this, so the time including this and this is 4t. Well, t plus t is obviously not 4t. So therefore you put 5t, because we're going constant along the line. So that's the second part. Now, what I want to just stress on that second part before we start drawing the third part is this A. Now we said A is 0 meters per second. Now, A is acceleration, is change in velocity over time. Our velocity is change in velocity, and this one, over time, on the y-axis. So therefore the gradient of this graph is going to be the acceleration. So, because we said there's a constant acceleration, so we draw a constant gradient. But there is 0 acceleration, hence no change in velocity, so 0 over whatever is over 40 is going to be 0, no matter what 40 is. That's just how math works. So therefore we get a line of a horizontal gradient, or no gradient at all. Now you don't need to mention that, it's just words out of my mouth. Okay, so then what you do is draw a constant downward sloping curve to reach the t-axis, x-axis, and therefore you'd put this point where it intercepts the t-axis as 5t plus 50, because it is this distance, whatever t is, 5t in terms of seconds, sorry, and it takes 50 seconds to get to rest, as we're told over in this section. Okay, so that's what you draw. Alright, so that's what a velocity time graph looks like in this case. Now, because we don't know what t is yet, you could, it doesn't really matter in proportions what you do it, just as long as it looks something like that. Now, as we find out, as we're going to find out at the end of this question, t is 8, but we'll explain how we get to that in a little bit. So really what you should be doing, if you do draw this diagram and you go, oh, when you find out what t is 8, and you've drawn the distance between 0 and t as the same as 5t plus 50, then, you draw the same distance as t, 0 to t is 5t to 50, then you need to change this bit and make it a bit greater, so this slope's a bit less steep. But it doesn't really matter, they're not that bothered as long as you've shown something like this. Okay? Now, one thing I want to also stress before we go on to the next question, so all these points will be helping you to understand the next questions. So that's question 8 finished, but the area under a velocity time graph, so how you'd work that out, you'd go, okay, well the area under, say, this point between t and 5t is 40 times 20, because that's the area of this little rectangle in the middle. Now, the area of that, velocity times time, if you were to put that in an equation, what you would get that as being the distance. Okay, so that's going to come in relevance in some later question, part C, I think it is. So that's part A, done and dusted. So that's what you should have for part A. And just to give you a bit of background, so if you want to have a go at the rest of the questions now, you couldn't do before, and I haven't gone through them, but I'm just giving you some advice for B and C. You should be able to do it now. But if not, you can carry on listening to my voice and hoping you make it through the video. Okay, so that's part A. We're going to have part B now. So part B says the total distance travelled by the car is 1,220 metres. So that kind of links in. We're going to be using exactly what we just talked about. So therefore, you'd put S, and you'd little brackets metres, equals 1,220 metres. This is sort of relating to physics, where you write everything down and you get given. Now we know all these different velocities, but they wouldn't have given us this graph if we didn't need to use it in some later question. Now we just said velocity times time is distance covered. Okay, so how do we work out the individual areas of these little shapes, the areas under the graph? Well, the first one, the one I'm going to shade in, this black area here, the black line weirdly enough. So I'm actually just going to call that A1, the second area A2, third area, weirdly enough, A3. So therefore what I'm going to say is the area equals the area of A1 plus the area of A2. Now you don't have to do this, you can just simply launch into answering the question, but I think it's nice. So if you do get the calculations wrong, you will get some method marks at least for being, I doubt many of you would be able to get this wrong. But you know, some people might. So what you do is you write area 1 equals area 2. So total area equals area 1 plus area 2 plus area 3. So sorry if that solves the stupid. I'm just going funny. Mind. So that's area 1 plus area 2. A2 plus area 3 plus A3. Okay, so to work them individual areas out, it's simple math, so a half times 20 times t. Plus, that's 20 times 40. Plus a half times 20, so it's changing, let's remember, half times 20 times 50. And as we know, the total area covered is equal to the distance travelled. So therefore we say this equation, so if we work this one out, so half times 20 times t is 10t, plus 20 times 40, that's plus 80t, plus a half times 20, which is 10, times 50 is 500. And we say 10t plus 18t plus 500. Now that's obviously 90t plus 500, but we say that is equal to 1,220 metres. So we simplify this down. So I'm going to do the long way around it. So therefore 90t equals 1,220 metres, take 500. So therefore, if you divide both sides by 90, therefore t is equal to 1,220 metres, take 500, and that's all over 90. Okay, so that's what your value of t is. That should come to 8 if I'm correct. Take 500. Yeah, so that gives you a value for t of 8. Therefore, t equals 8. Now, that's part B. So, as I said, that was just using the idea of area under a graph is equal to area under velocity time graph is velocity times time, which is distance covered. So obviously, if you've told the distance covered, it's going to have some relevance. Now, one way you could do it if you wanted to was use Suvat equations to work out the individual distances at each stage. So the distance covered in the first stage, second stage, third stage. But that's going to be might get yourself into a little bit of a mess with that one. I tried that and I did get into a bit of a mess. I think this idea is a lot simpler. But if you didn't get this idea, it is possible to use Suvat equations in this sense. But as I said, I wouldn't, because you don't know the acceleration, really. You don't know enough information. And you might be able to do it, but I wouldn't advise it. This is a lot simpler. Okay, so part C, 3C, says find the initial acceleration of the car. Now we said this is the initial part, the middle part, and the last part, think of it like that. So the initial part, so we know, obviously, as we knew before, the initial speed, u, is equal to 0 metres per second. The final speed is equal to 20 metres per second. And we now know t1 is equal to t. So as t is 8 seconds, therefore the time period is 8 seconds. So you could put change in velocity is equal to 20. So therefore, what I would always show, some students probably don't do this, is show this, because we know, obviously acceleration is change in velocity over time. It's a rate of change of it. Yeah. So acceleration is the rate of change of velocity. Now many students would just go and say, okay, a equals v, take u over t. Now it's quite a risky move, because you may not realise it, but you are skipping out a step. We don't just come up with that equation randomly. We use Suvat equations. And one of the Suvat equations that involves acceleration is v equals u plus at. This is the one you rearrange to get acceleration. Now if you press for time in the exam and you come back to this with 2 seconds to go, I wouldn't write that in. But if you're following this through, then this should be fairly simple. And I say you might have 2 seconds to go, because you might not have got this bit, and you'll go in the last second of the exam, like I do, and think, I've got another 3 questions to answer now. So anyway, as I said, you'd write this, and you'd rearrange it to get a, which gets you the equation, v equals u, v take u over t equals a. Put in what you know, so therefore you could just put a is equal to 20 over 8, which is 5 over 2, or 2.5 metres per second squared. I said it when I wrote it down, metres per second squared. Okay. Now the reason we could do metres per second squared is because v is in metres per second and t is in seconds, and that's essentially s to minus 1 on the bottom. So therefore minus 1 take 1 is minus 2, so that's we get metres per second squared. Okay? So that's just a bit of background. So just let me double check that's correct. Sorry. Yeah, okay. So that's the right answer. So, as I said, a quick recap of this question. Essentially, what we did was we drew a velocity time graph and said, okay, well, just inputted our information into. I selected each stage, so the first stage, the second stage, and the third stage. I just called them U1, V1, U2, V2, and U3, V3. But you could call it initial, final, middle, and final. But I think that's a bit confusing considering you've got initial speed like 3 times. And use that information to draw ourselves a graph. And remember, one of the key things I said about 3A was, obviously you can turn off now if you understand this question, but this is just a recap for those of you who don't, or want to listen to my voice a little longer. Lord help those who do. So anyway, we said, be careful, the change, this is a total time, this is not the change in time. So therefore, we said the first one occurs in t seconds. So you write 0 t, and that's the change of 0 to 20. It's a constant acceleration, get a constant gradient, because velocity over time is acceleration. Yeah, so we've got a constant gradient. And then we said, so using the idea of this is a constant time, so therefore the distance between the 2 stages must be the difference between the stage. So you add, so t plus 4t is 5t, because that is the total time, of the time here, plus the time here, plus the time here. And then to get to the final bit, you add all 3 times together to get to the last part of. So if this is making no sense, you could just switch off. Well, I'm just trying to explain it a slightly different way. And we recap what each bit of the graph showed us. We said the error under the graph was distance, because velocity times time is distance. So therefore we said, okay, we can use the individual areas under the curves. As we told, that was equal to 1,220 metres. Simplified it down, rearranged to get t. We've got t was 8. And as we know, the acceleration is a gradient of the graph. So we are asked to find the initial acceleration. Was the only point of acceleration. So you couldn't really get that one wrong, because this has no acceleration and this has negative acceleration, or what we call as deceleration. So therefore, as this is constant, you know, u, v, and we now know t. We didn't before, but as we said, we just found out t was 8 from rearranging this equation. And then I said it'd be a good idea to use the Suvat equation to show where you get the equation for acceleration, just in case you get that one examiner who hates you and wants to lose your marks because you say, haha, you can't lose me any marks. I've rearranged the acceleration equation. Velocity equation to get acceleration. And input what you know, and you get an answer of 2.5 metres per second squared. And I explained how you got seconds per second squared. Okay, so that's question 3 from November 2002, Mechanics Unit 1 at Excel. So thanks for watching, hope that's helped, and hopefully we'll see you in another video sometime, and I've not killed you all off just yet. I'll do that just before the exam, so help you out there. Thanks for watching, and we'll see you in the next video.